Swayam Prabha. Digital India. Educated India.
In the last lecture, we discussed about the frequency domain solution of the single and multi-degree of freedom system, and in that we discussed about the obtaining the frequency contents of the ground motion, and with the help of that frequency content of the ground motion, we solved the problem in frequency domain, obtain the frequency contents of the response, and then inverse Fourier transform it to obtain the time history analysis. For the multi-degree of freedom system, we require the R matrix, whereas for the single point excitation system we require I matrix or I vector, whatever be the case. Now, here is an example problem which illustrates how we can obtain the response of a multi-degree of freedom system using both time domain and frequency domain. In a multi-degree of freedom system, for example, in this frame we have three ground accelerations, and these three ground accelerations are different, although the same earthquake wave is passing through all the three supports, but because of the time delay that has been assumed, the excitations at the three supports would be different. So, in order to understand that, we take 30 seconds duration of the ground motion, and which is travelling. When it arrives here at this particular point, then the ground motion at this point would be 0, and next here also it will be 0. When 5 seconds of ground motion has passed through this particular point, then we get the ground motion over here, and at that point of time ground motion still at this point is 0. When 10 seconds of ground motion have passed through this point, then we get the ground motion here as well. So, as a result of that, the excitation caused by the same travelling wave of ground motion is different at these three different supports, and we can obtain this by the following considerations from the 30 seconds of record of ground motion that is available to us. The last 10 seconds of record have 0 values for the first support. That means, when all the 30 seconds have passed through this point, then we have the next 10 seconds of the time history of excitation would be 0. In this case, the first 5 seconds and the last 5 seconds have 0 values, and in between we have got the 30 seconds of the ground motion, and for the last support we will have the first 10 seconds will have 0 values, rest of the 30 seconds will have non-zero values. As a result of that, effective total duration of ground motion is taken as 40 seconds, and that is how the 3 different records of excitations differ on a scale of measurement of 40 seconds. Now, with these 3 ground motion, distinct 3 ground motions, we write down the equation of motion for the system. This has 2 non-support degrees of freedom, and the support degrees of freedom are 3, and they are shown over here. That is these are the 3 ground accelerations, and the R matrix we computed before as 1/3, 1 1 1 1 1 1. So, for this particular problem, we had seen before that the participation of the ground motions in creating responses at the 2 non-support degrees of freedom were equal and was equal to 1/3, 1/3, 1/3. So, this was of course for this problem. For other problems it may not be like that. That is what you have seen before. The R matrix could be different for different kinds of structures, and it is to be obtained from the matrix condensation relationship. Now, with this particular equation, now we put on the values of x double dot g1, x double dot g2 and x double dot g3 in time from the different records that we have obtained, and these records are used for solving the problem in time domain using Newmark's beta method. And when you use the Newmark's beta method using direct integration technique in the recursive form, we require the C matrix, and the C matrix is obtained with the help of these 2 coefficients alpha and beta, and this is the Fn matrix of the Newmark's beta method, and this is the Hn matrix for the Newmark's beta method. The initial condition that was used is equal to 0 velocity and 0 displacement. With the help of that, we went for the recursive equation, solution of the recursive equation to obtain the response of the system. In order to remind you what is the form of the recursive equation, let us have a look at the recursive equation. So, that this was the recursive equation that we use for Newmark's beta method. So, this is Fn matrix and this is the Hn matrix. So, plugging in the different values that we use in the solution of the problem, we get the solution, and we get relative displacement, velocity and acceleration. The displacements at u1 and u2, that is the 2 non-support degrees of freedom, the time histories of that are shown over here. It can be seen that although the 30-second is the duration of the earthquake, but the excitation duration was effectively 40 seconds, and therefore, the response that we get at u1 and u2 are extends beyond 30 second, and it almost goes to 40 second. Of course, in this part the responses are very, very small. Next, we solved the pitch roof portal frame, and here if you recall, in the pitch roof portal frame we had the degrees of freedom, one in the horizontal direction and other at the crown in the vertical direction. These were the 2 degrees of freedom, and for that we assume the 5 second time delay between the two supports. By solving the eigenvalue problem, we get the frequency as omega 1 and omega 2 as these values, and from that we computed alpha and beta as that, and delta t was taken as 0.02, and this is how we obtain the R matrix. If you recall, that is, we give a unit displacement over here and find out what is the forces developed here and here, that gives the stress stiffness matrix, and from that one can obtain the value of the displacements caused at these points due to the unit displacement. Similarly, if we give a unit displacement over here, one can find out what is the vertical displacement here and what is the horizontal displacement over here, and they constitute the R matrix. That is what we had shown for this example when we are working out the R matrix for different structures. And the degrees of freedom, let me repeat again, is the horizontal degree of freedom here 1 and the another horizontal vertical degree of freedom over here. These are the 4 and 5. So, we calculated the mass matrix. This calculation was shown. How do we calculate this mass matrix for the pitch roof portal frame? This is the stiffness matrix, condensed stiffness matrix corresponding to the two translational degrees of freedom, and this is the R matrix that we obtained for the 2 degrees of freedom again. So, now by writing down the equation as mx double dot plus cx dot plus kx is equal to minus mr into x double dot g, with the using that we obtain the response of the system. But before that, let me tell you that in this case, although the duration of ground motion on earthquake record is 30 seconds, but the duration of excitation at the two supports are taken as 35 seconds, because there is a 5 second of time delay between the two support, that is what is assumed. Therefore, in the first case, there will be the first 30 seconds will be non-zero values and the end 5 seconds will be 0 values. For the second support, the first 5 seconds will have 0 values and the next 30 seconds will have non-zero values. That is how we construct the 35 seconds of excitation for the two supports, and we use these two excitations and obtain the values. Now, in this problem, it was solved for two cases. In one case, we considered a time delay, and in another case, we obtain that we assume that there is no time delay between the two supports. So, this is the result shown for the without time delay case, that is, in both the supports we had the same ground motion of 30 seconds, and we continued the integration till 35 seconds. So, after 30 seconds, the responses that we see is due to the free vibration of the problem, and the U1, rather the degree of freedom 4, that is the horizontal degree of freedom, we see that the ground displacement or the displacement of the response is about 0.075, whereas the vertical response at degree 5, that is of the order of 2 to the power 10 minus 3. It is expected because since the ground motion is in the horizontal direction, therefore, the vertical response of the structure would not be very high, and therefore, we get a low value. This is the scenario when we have got the time delay effect considered in the analysis, and we see that there is a difference, of course, between this case and the previous case. That is, in the previous case we had 0.075 almost at the maximum value. Here the maximum value it goes up to 0.048 or so. So, we see that there is a with time delay the response is reduced. That is expected whenever there is not a perfect correlation of the ground motion between the two supports, the responses, at least the displacement responses generally is decreased. And but the important thing is that we see that the vertical in the vertical degree of motion the responses has increased, that has become nearly equal to 4 into 10 to the power minus 3, where in the previous case it was almost near 2 into 10 to the power minus 3. So, we see that the horizontal in the horizontal direction the response of the structure is decreased due to the time delay effect, whereas in the vertical direction in which the ground motion is not acting. So, in that vertical direction the response of the structure is increased. Next, let us come to the state space direct analysis, and we have written down the equation of the state space before, and in that we have an A matrix and F matrix, and the form is equal to Z dot is equal to A Z plus F, if you recall, where A is a matrix, Z is the state of the system consisting of x and x dot, that is a displacement and velocity. Now, here this is for the single point excitation system, this is not R, this should be I, that is influence coefficient vector, and this is for the multi point excitation system, this becomes R into x double dot g, that becomes the force. And the first part, that means this vector is of size 2n. If it is n degree of freedom, then the vector will be of size 2n. So, first n values will be 0 and the last n values will have minus r minus I into x double dot g over here, and here it will be minus r into x double dot g. And how we construct r into x double dot g, that you have explained in the previous problem. So, we can solve the problem for the system in time domain as well as in frequency domain, and in the time domain one can solve the problem in using the Newmark's beta method or Duhamel integration for a single degree of freedom system. But when we solve the same problem in for multi degree of freedom system, generally we are not able to solve the problem using Duhamel integration. So, there is a problem, and therefore, we generally do not try to solve the problem using Duhamel integration for multi degree of freedom system when we try to solve it in the state space form. So, in that case we generally use some other integration scheme than the Duhamel integration. This problem in the state space can also be solved in frequency domain, and in the frequency domain what we do is that we try to find out the H matrix, that is the frequency response function of the system. So, let me first clarify this. Say this is the equation, Z dot is equal to Az plus Fg, and we say that we are able to Fourier synthesize this Fg, which is described in time. Mind you, Fg is a vector, and the top values are 0 and the last values have got non-zero values corresponding to the time history. Then this FGT can be Fourier synthesized and can be written in this form FG I omega into e to the power I omega t. FG I omega can be easily obtained from using the FFT algorithm that we discussed before. Now, if the excitation is of this form, then it is reasonable to assume that the steady state solution of the system would be also of this form, Z will be equal to Z I omega into e to the power I omega t. Now, if we substitute this into this equation, that is we differentiate this once, then the differentiated form will be equal to this capital I cap omega Z I omega e to the power I omega t, where the I cap is nothing but a matrix with all diagonals at imaginary imaginary quantity I and the non diagonal components are all 0. So, this is the definition of your I cap with omega multiplied by Z I omega into I e to the power I omega t. So, that becomes the Z dot, and in the case of Z we simply substitute this value. So, we have got A multiplied by Z I omega e to the power I omega t, and for Fg we write down the FFT of Fg. Then if I take this onto the left hand side, then we get this particular matrix I cap omega minus A into Z I omega, that becomes equal to Fg I omega, because e to the power I omega t cancels from both sides. And then one can write down for a particular frequency, say a jth frequency, if we can write down J I omega to be is equal to I cap omega minus A inverse of that into Fg omega, and this is what is called Hj I omega, capital Hj I omega for the jth frequency. And Fg I omega can be obtained from the FFT that I told before, and how we get the individual components or the elements of this vector when we have the R matrix that we had discussed before. That means the one element, typically one element of this vector would be of the form of R11 x double dot G1 plus R12 into x double dot G2 and so on. That will be the one element, and in time one can compute this and can get a particular value in time, and that is how we can have all the elements, values of the elements at every instant of time t that we feed in the FFT. So, we have to now carry out FFT for the n number of time histories, because here we will corresponding to all n degrees of freedom we will have one excitation. So, we will have n time histories which are inputted into the FFT algorithm to find out the vector of Fg I omega. Now, with this background, so for the jth response quantity in frequency domain, we can write down this relationship, and Hj I omega is defined like this, that is what we explained before. And then once we get the value of Zj I omega, then for different values of omega we obtain this Zj till the Nyquist frequency or the cutoff frequency, and then after that we add on the complex conjugate values, that is again what we discussed before, and that entire values of or the values of the Zj omega at a interval of delta omega. So, all the values including the complex conjugate values, that are given in IFFT, and the IFFT gives the value of ZT. And the ZT contains not only the displacement but also velocity as well. So, that is how one can solve the problem in state space in frequency domain. So, now we look into another example in which there is a pipeline, and in this pipeline is lying on the ground. The resistance provided by the ground is represented by the springs over here, and the damping provided by the soil, that is shown here as a dashpot. So, at these three supports we provide the equivalent spring and dashpots for the soil, and these are the masses which are lumped at these three points, and we have got 3 degrees of freedom in the vertical direction 1, 2 and 3, and a rotation here. So, what we do first is that we condense the rotational degree of freedom, we condense out, and then have only a 3 by 3 matrix corresponding to this vertical 3 degrees of freedom with these values which are specified over here. Next we obtain this is the K matrix which is obtained, this is the C matrix which is obtained using assuming it to be a classically damped system, and in which the values of alpha and beta are these. So, with these values the C matrix is generated. Then we form the A matrix, and this becomes the FG matrix, and since we assume that the ground motions at these 3 supports, they are same, that means there is no time lag between them, that is why we have 1 1 1 over here, this is minus 1 1 1, that is the last 3 values are this, and the top 3 values of course will be 0. Then we Fourier synthesize these FG, and once we Fourier synthesize these FG, then one can obtain the values of the responses of the 3 displacements in frequency domain, that is Z, J omega, and using IFFT we obtain the response of the 3 degrees of freedom in time domain. So, this is the time history of the displacements for degree of freedom 1, that is shown. Then we have the time history of displacement at 2 and time history of displacement. This is 1 and 2, these 2 are shown, and this result is for the solution that we obtain by solving the equation not in the state space, but by solving the problem in the as a second order differential equation. There also we can obtain the solution in the frequency domain. So, the objective of this problem was to solve this problem by 2 methods, that is using the frequency domain ordinary and state space solution. So, ordinary means the solution of the second order differential equation, and the state space solution is the one in which the Hj matrix is different than the Hj small Hj matrix that we obtain for the second order differential equation. So, and the results you can see that they compare very well. That is the displacement of degree of freedom 1 over here has a maximum value of almost 0.05. There you can see that again the maximum value is almost 0.05. So, the responses obtained by the ordinary solution of the ordinary differential equation, the state space equation, they are obtained as same. Next, if we are wanting to solve the problem for absolute displacement, then we use a different equation, and in that different equation on the left hand side of the equation you have all the terms written in terms of the total displacement, that is total displacement, total velocity and total acceleration. On the right hand side, instead of the acceleration, we require the knowledge of displacement and the velocity that we discussed before, and generally we assume that these CSG, that is the coupling term in the damping matrix, they are generally set to 0 because that is very small, and in most cases we only consider Pg to be equal to minus Ksg into Xg. So, by knowing not the ground acceleration, but the ground displacement, one can obtain the value of Pg vector over here. And once we know the Pg vector, then we can solve the problem either as a second order differential equation or in the state space, and we can use whatever method we want, that is we can solve it in time domain or in the frequency domain. Now, we come to what is known as the modal analysis, which is very popular in the dynamics. In the beginning of the multi-degree freedom system, I mentioned that the solution for the multi-degree freedom system can be obtained for two kinds of excitation. One is for the single point excitation, other for the multi-point excitation. Again, for both types of excitations, we have a direct solution and the solution obtained by modal analysis. When we use the direct solution, then we require the C matrix to be defined, and for defining the C matrix, we assume that the damping matrix is of classical nature, or we say that it is a classically damped system. And when we assume it to be a classically damped system, then C matrix is written and to be is equal to alpha times m plus beta times k, where alpha and beta values are obtained for using the two frequencies of the system. Generally, the first two frequencies are considered to obtain the values of alpha and beta. So, once we have the C matrix for the system, then one can go ahead with the direct solution, either solving it as a second order differential equation, or by solving it as a coupled of first order differential equation, which is called the state space equation, and one can use both time domain solution and the frequency domain solution. In the time domain solution for multi degree of freedom system, we generally adopt Newmark's beta method for solving the problem. Duhamel integral is somewhat what we call complex if we extend it to the multi degree of freedom system. Now, we come to the modal analysis, and in this analysis we try to take advantage of the properties of the mode shapes or undamped mode shapes of these structures. And I am sure all of you know from the knowledge of your dynamic analysis how we carry out the modal analysis, but still for recapitulation, let me try to summarize what you have already learnt in your dynamics for the modal analysis. We write down the displacement, that is the x are the dynamic displacement of a multi-degree of freedom system, that as equal to a phi matrix, that is a mode shape matrix multiplied by z, which are known as the generalized coordinates, or sometimes also known as the modal coordinates. So, with this defined, we go to the main second order differential equation. We substitute in the main equation the phi into z in place of x. So, once we do that, then this becomes m into phi multiplied by z double dot. The C matrix becomes C into phi into z dot, and this one becomes phi k into phi into z. So, in place of x we write phi z, here in place of x dot we write phi z dot, and here in place of x double dot we write down phi z double dot. Once we do that, then we pre-multiply by the transpose of the phi matrix, and once we pre-multiply by phi t, then here we get a term as phi t, here we get phi t, here we get phi t, and on the right hand side also we multiply it by phi t. Now, for a single point excitation system it will be I, for a multi-point excitation system it will be R. Then comes the property of this phi t m phi and phi t c phi and phi t k phi. The mode shapes of the undamped system obtained by solving the eigenvalue problem, that is k minus m omega square, absolute value of that will be equal to 0, or in standard form it is written as Ax is equal to lambda x, and we give this A matrix into the in any standard program for eigenvalues, and then it gives the eigenvalues and eigenvectors of matrix A. So, those eigenvalues and eigenvectors are nothing but the mode shapes and the frequencies of the system. Now, the property of these eigenvectors or the mode shapes are that it is orthogonal with respect to K matrix and it is orthogonal with respect to mass matrix. Orthogonality condition means phi t k phi will lead to a diagonal matrix, that is this will be having only a diagonal values as non-zero, all of diagonal values will become 0. So, this turns out to be a diagonal matrix. Similarly, M matrix becomes a diagonal matrix because this is also orthogonal with respect to the mass matrix. Now, if one assumes that the C matrix is proportional to the alpha times m or is proportional to mass and stiffness matrix, then one can write as C is equal to alpha into m plus beta into k. Therefore, phi t c phi also will become diagonal because phi t k phi will be diagonal, phi t m phi will be diagonal. So, therefore, this phi t c phi also becomes diagonal. Now, if the left hand side of these things becomes diagonal, then we can see that in the left hand side the equation of motion becomes uncoupled. Uncoupled in the sense that only you have diagonal terms over here. So, each one of these equations are independent of each other, that is one can write down a equation only in the form of this, that is this m bar I into z double dot I, c bar I into z dot I, k bar I into z I. This is the ith equation, and this is a single variable, z I is a single variable, and one can write down such equation which is consisting of n number of equation, that is I varies from 1 to n, where n is the degree of freedom for the multi-degree of freedom system. So, this is the basis of the modal analysis, and if the k bar I and m bar I that are taken, and we divide k bar I by m bar I, then we get the frequency, natural frequency square, right. That is the ith natural frequency we get like that, and one can write down c bar I that is to be is equal to twice into twice xi I omega I into m bar I, and if we divide all through by m bar I, then we land up in a equation in a single degree of freedom equation in which it is defined with respect to frequency of the mode, ith mode, and the damping of the ith mode. Generally, we assume the constant damping for all the modes, therefore, we do not write down here xi I, but we write simply xi, indicating that it does not vary with modes. Then on the right hand side, the entire thing, this is phi I t m r into x double dot g, that can be written as a summation of lambda I k multiplied by x double dot g k. Now, the k indicates the supports. That means, in a multi degree of freedom system, if you have got s number of supports, then these s number of supports can be considered in the analysis, and these at these n supports we have different ground accelerations, that is represented by x double dot g k. K stands for the number of the support. So, this x double dot g k varies from support to support, and lambda I k is a quantity which also varies from support to support. So, here we have got lambda I k defined as phi I t multiplied by m into r k, where r k is the ith column of the R matrix. So, divided by phi I t m phi I. So, that is the definition of lambda I k. So, it is support dependent, that is it has an index k. So, this summation is done for all the supports over here, and we generate a time history of the ground excitation for the structure. That means, for the entire structure, for the ith generalized coordinate, we will have only one time history of excitation, which will be called the generalized excitation for the ith mode, and there the effect of the different types of excitations at different supports will be all summed together to find out the time history of the generalized excitation at the ith mode. So, now we can solve these equation written in terms of the general coordinate, or we call this modal equation we can solve. as a single degree of freedom equation, either in time domain or in the frequency domain. In time domain again we have option, we can use Duhamel integration, or we can use Newmark beta method, or we can use any other integration scheme. Let me just try to elaborate this lambda I k. If the ground acceleration is not varying from support to support, that means at all supports if you have got the same excitation on time history or the ground acceleration, then in place of r k it becomes I, that is the influence coefficient vector 1 1 1 1. In that case it becomes the k, it becomes independent of k, and we have a unique value of lambda I defined for the ith mode. So, that quantity is known as the mode participation factor that has been discussed, I am sure, in your dynamic analysis class. So, for the single point excitation you have this mode participation factor as a single quantity, but if it is a multi support excitation system, then there is not a single value of the mode participation factor. This mode participation factor then becomes support dependent. That means, for each support we have one mode participation factor defined. Obviously, if S is equal to 1, that is if you have got a single support excitation, then this generalized formulation can be made what to call made same as single point excitation system. Now, let us look into the example, an example solved for these multi support excitation system with the modal analysis. So, here we take the example of the cable stayed bridge. If you recall, in that cable stayed bridge we had the many supports, or rather 4 supports were there in the cable stayed bridge. Let me show you the diagram for that for your recapitulation. Yeah, this is a cable supported bridge that we have taken up in order to obtain the R matrix, and in that you can see that we have got one support, second support, third support and fourth supports. At these 4 supports the ground accelerations were different, and the degrees of freedom that we considered were 3 degrees of freedom, that is at the 2 top of the towers or the at the top of the 2 towers we have got 2 horizontal degrees of freedom, and the vertical degrees of freedom is considered at the center of the deck. So, these were the 3 degrees of freedom, dynamic degrees of freedom that we considered. So, we condensed out all the rotational degrees of freedom, then we obtain an equation or obtain an expression for the stiffness matrix and the mass matrix corresponding to these translational degrees of freedom, and then from the stiffness matrix we again took out the 3 non support degrees of freedom, that is 1, 2, 3, and the rest were the support degrees of freedom, and from there we constructed the R matrix for the system, and the R matrix for the system was obtained like this. This was the R matrix corresponding to all the 4 support degrees of freedom, and the R matrix obviously was 3 by 4 because the 3 are the non support degrees of freedom. So, with this R matrix in position, we try to solve this problem, and the solution for the problem, the solution for the problem were obtained with the K matrix, that is the for corresponding to non-support degrees of freedom, that was the K matrix that was obtained, and the mass matrix was a diagonal mass matrix because we lamped the masses at the 3 degrees of freedom, and then this was the R matrix that I had shown you before, and then omega 1, omega 2, omega 3, 3 frequencies were obtained. The phi 1 t, phi 2 t, phi 3 t, that is the 3 mode shapes were like this, and then we have the first modal equation that we can write in this particular form. Now, you can look at the nature of the mode shape. It is interesting to see the nature of the mode shapes. So, the nature of the mode shapes is the first mode basically is such that you have these are the first 2 degrees of freedom, that is at the top of the pylons, and you can see that in the top of the pylons, if one is moving in this direction, the other moves in this direction. That is you have a situation like this, and with at the center we have a downward upward displacement. So, the phi 2 basically were such that both the pylons are moving in the same direction, and there was no what you call displacement at the center, and this basically is again a mode shape in which the both pylons moved in the opposite direction, and the deck, center of the deck moved down rather than up. So, these were the 3 mode shapes that were obtained. So, using these 3 mode shapes, so we write down the 3 modal equation, and for these 3 modal equation, these are phi 1 t m, and this one will be equal to R 1, not R 1, that multiplied by G, that would give the rho G 1. So, this is the value of the generalized ground acceleration or generalized excitation of the first generalized equation, and with a delta t defined as 0.025, this thing can be integrated. But in order to obtain the values of x double dot g 1, x double dot g 2 and x double dot g 3 and g 4, for that we take the ground acceleration of 30 second, which is travelling, and there is a 5 second of time delay between the supports. As a result of that, you will have for the first support the 30 seconds of the record, first 30 seconds will be non-zero, and rest 15 seconds will be 0 values. Similarly, for the second support, you will have first 5 seconds as zeros, then you will have got 30 seconds of the record, and the last 10 seconds will be 0. So, that way we can construct the different excitations at different supports from the 30 second of the actual earthquake that is travelling, and with a 5 second time delay between each support. So,